In this video, we're going to take a look at a binomial probability distribution. So let's first start off by describing what a binomial probability distribution is. It's a distribution that shows up really pretty frequently in the real world. A binomial probability distribution, it satisfies 4 different requirements. So the first requirement is the procedure should have a fixed number of outcomes, or fixed number of trials, right? So a trial is a single observation. So if you don't know going into it how many trials you're going to have, it's not binomial, right? So if you're saying we're going to stop when we see a certain number of successes, that's not a binomial because you don't know how long until you see that number of successes. If you say we're going to stop after 12 trials, that is potentially a binomial. It at least has a fixed number of trials. The second is the trials must be independent. And so when we say trials are independent, that means that the outcome of one trial does not affect the probabilities of the other trials. Right? So if we know we have a success on a single trial, it does not affect the probability of success on the following trial or any of the subsequent trials. The third thing is each trial must have 2 possible outcomes classified into 2 categories. Right? So this is why we call it binomial, the prefix bi meaning 2. So we have 2 possible outcomes for each trial. We usually refer to these as success and failure. When we talk about them as success and failure, this is not what we would necessarily, statistical success is not going to be the same as like real world success. Some things when we're trying to detect a disease, we might say we were successful in detecting a disease where that's actually a bad thing. So don't think of them as good and bad. It's just, did this thing happen? Was there a success? Were we able to find this thing that we were looking for? And then the probability of success, it must be fixed or equal for each trial. So from one trial to the next, the probability of success should be the same. So let's take a look and see if we can determine if some of these things are binomial distributions in a moment, but let's talk about notation first. For probability of success, P of S, we will use a lowercase p. For a probability of failure, we will use a lowercase q. And since there's only success or failure on a single trial, the probability of failure is 1 minus the probability of success. Right? So if you're successful 20% of the time, then it's a failure 80% of the time. We use a lowercase n to represent the fixed number of trials. The specific number of trials, specific number of successes in n trials, we use an x, although depending on what you're looking at, other books may use other notation, but we will use the letter x. P of x, capital P of x, will denote the probability of getting exactly x successes. So P of 2 is the probability that there are exactly 2 successes. All right, so let's look at this. Determine if the following gives a binomial distribution. If it does, determine the values of n, p, and q. If not, state which of those 4 requirements it fails. So a person flips a coin until they get 3 heads. The random variable x is the number of tails they observe prior to the 3rd heads. So is that binomial? So we have our 4 different things we need to check for. Does it have a fixed number of trials? Do you know how many times you're going to flip the coin? Well, we're going to flip it until we get 3 heads, but that could be after 3 coin flips, or 4, or 5, or 6, or 6,000. So this is not binomial. It fails for sure 1. Are the coin flips independent? Yes. If you flip one coin, the probability the next one is heads or tails does not change. So you have independence. Each coin flip is either heads or tails, so there are two outcomes. And the probability of heads is 50% for each of them. Probability for tails is 50% for each of them. Or at least really close to that. You can look at other studies, scientific studies, and you can find that maybe the probability is ever so slightly biased towards one direction. Our next example is this. When an American adult is selected with replacement, so we're going to choose a randomly selected American adult, ask them a question, put them back. It's possible we will select them again. There's a 13% chance that he or she uses Twitter. The random variable X is the number of Twitter users among 8 randomly selected adults. And so here, is this binomial? Yes, it is. Does it have a fixed number of trials? Yes. There are 8 trials. We're going to select 8 people, so the value of n is 8. We will consider it a success if they use Twitter, and not a success. We'll consider it a failure if they do not. You may, again, think about it as the opposite. You might consider it a success if they don't use Twitter, and a failure if they do use Twitter. But for our purposes, we will say P, the probability of success that any one person we randomly select, the probability they use Twitter is 13%. Probability that they do not use Twitter is 1 minus 0.13. So 1 minus 0.13, which is 0.87. So we have a fixed number of trials. The trials are independent. If one person uses Twitter, then when we randomly select another person, they are no more or less likely to use Twitter. So we have independence. Every person either uses Twitter or they do not use Twitter. If they sort of use Twitter, then they use Twitter. And then the probability of success is equal from trial to trial. In our next video, we're going to take a look at performing some calculations associated with binomial distributions. We will see you there.